Alright, in this video we're going to be looking at some of the applications of normal distributions. We already talked about the standard normal distribution where the standard deviation was 1 and the mean was 0. Now with this we're going to be looking at methods that we can work with for a normal distribution that has any mean and any standard deviation other than 0 and 1. Okay, so in this case, let me start off with a procedure for a non-standard normal distribution. And of course, for a non-standard normal distribution, that means that the mean is not 0 and the standard deviation is not equal to 1. Okay, it can be any number other than 0 and 1 for the mean and standard deviation respectively. So the procedure of that is this. It would be best to sketch a normal curve. Okay, and when you sketch the normal curve, you want to label the mean and any x value that is given to you. And then you're going to shade the region for the desired probability that you're trying to get. Let's say for the desired probability. So that's step number 1. Alright, step number 2, for each x value, what you're going to do, you're going to convert to an equivalent z-score. And if you recall, I'll go ahead and give you this formula for the z-score. Okay, because back in chapter 3 we talked about how to convert any x value to a standardized z value, which is going to be this case x minus mu, which is the population mean, divided by sigma, and that's the population standard deviation. Your mu is the mean, sigma is the standard deviation of a population, and that z value will be rounded to 2 decimal places. The reason for that is this. When we use our standard normal distribution table, or table A-2, your z values will always be to 2 decimal places. Okay? And then step number 3, you're going to use, and for those of you who are taking my class, you'll know that I'm talking about table A-2 that you can find on Cruiser. And for those of you who don't know what table A-2, that is the standard normal distribution table. And you'll use that to find the area of the shaded region. And keep in mind that area is always going to be the probability value. So here, keep in mind that area and probability do have relationships. Okay? So what I'm going to do here is look at a few examples of just this. Okay? So here's the first example. Let's say we want to find the area of the shaded region. We want to find the area of the shaded region. The graph to the right depicts IQ scores of adults, and those scores are normally distributed with a mean of 100 and a standard deviation of 15. Okay. So in this case, if you look at the shaded area to the left is what we're trying to find. And here we have a x value, in this case, of 115. So in this case, we already know that the mean is 100. That's your mu. The standard deviation, which is your sigma, that's 15. Your x value is 115. So the first thing we have to do here, well, we already got the graph given to us, and it's already shaded. So now the next thing we need to do here is convert 115 to a standardized z value, which will be x minus mu divided by sigma. And in this case here, your x is going to be 115 minus mu, which is 100, divided by sigma, which is 15. Okay, simplify the numerator. You got 115 minus 100, that's going to give you 15, and then 15 divided by 15 will be 1.00. Okay, so the z value to two decimal places will be 1.00. Okay, so now we look under the standard normal distribution table. In this case here, 1.00 is positive. So if you recall in the last video, we look for 1.00. Okay, 1.0 is on the left. The zero, that second zero, is this first column right here, 0.00. So 1.0 and 0.00, if you read to the right and read down, you'll see that it's going to be 0.8413. Okay, that's the area to the left, which is what we're trying to find. So we can conclude that the probability that your x value, and it's shaded to the left, so that means less than 115, that probability will be 0.8413. Okay, and that's this shaded area to the left. That shaded area is 0.8413, which is also the probability that, in this case, a IQ score of an adult is less than 115, 0.8413. Okay, next example looks like this. Now we got two IQ scores, and here we want to find the area of the shaded region. The graph to the right depicts IQ scores of adults, and those scores are normally distributed with a mean of 100 and a standard deviation of 15. So here we know what the mean is. That's 100. The standard deviation, sigma, that's 15. Now we got two scores. One is 75 and the other one is 100. Okay. So I'm going to start off with for x equals 75. The z-score on the left, I'm labeling this as z sub l. That's the z-score on the left. Of course, we use x minus mu divided by sigma. That x value is 75 minus your mu, which is 100, divided by sigma, which is 15. Now, if you do 75 minus 100, that's negative 25, and negative 25 divided by 15 will give you negative 1.67. So we know the z-score for 75 is negative 1.67. And then for x equal to 110, that's a z-score, that's a x value on the right, so that z-score on the right would be this. Still x minus mu divided by sigma. This time your x is 110 minus 100 divided by 15. Well, 110 minus 100, that's 10. 10 divided by 15 will be 0.67. Okay, so we know what our z-scores are. For 75, it's negative 1.67, and for 110, it's going to be 0.67. Now, for each one of those, we're going to use the standard normal distribution table. We do for this one, this is negative 1.67. So we use negative z-scores, and we're going to find negative 1.67. So here's negative 1.6 right here, and 0.07 is this column right here. So if you read across and down, that area will be 0.0475. Okay, so here for negative 1.67, that area is this 0.0475. And then for this other z-score of 0.67, which was 110, 0.67 is positive, so we go to the positive z-score part of the standard normal distribution table, find 0.6, and then 0.07. That's this column here. So read across and down, you'll see it's 0.7486. So for 0.67, that area is 0.7486. Okay? And of course we got the area in between, so that means we need to subtract these two probabilities. So here we can find the probability that your x value is between 75 and 110. That's going to give you 0.7486 minus 0.0475, and that will give you 0.7011. So here, the probability that an adult IQ, randomly selected adult IQ, is between 75 and 110 would be 0.7011, meaning there's a 70.11% chance that a randomly selected adult will have an IQ score between 75 and 110. Okay. All right, now let's look at the next example. Okay, it's this one. And in this case here, we want to assume that adults have IQs that are normally distributed with a mean of 105 and a standard deviation of 20. Find the probability that a randomly selected adult has an IQ less than 133. Okay, so here we want to find the probability that an adult randomly selected has an IQ less than 133. Now this time we're going to have to draw a normal curve so that we can get a picture of what's going on here. In this case here, our mean was 105, so that's your mu. Standard deviation in this case is 20. And 133 is this value on the right hand side of 105. Now, less than means that we're dealing with the area to the left of 133. So in this case, that's this shaded area in green. Okay, so that's the shaded area that we're looking for. And when we use the standard normal distribution table, whatever we get in that table is that shaded area to the left. Okay, but we first have to convert this to a z-score. Okay, so here this x is 133. So its z-value, or standardized z-value, as x minus mu divided by sigma. This time x is 133 minus mu, which is 105. All that's divided by 20. Well, 133 minus 105, that's 28. So now 28 divided by 20, that's going to give me 1.40. So your z value is going to be 1.40. Okay. Now I can go ahead and use table A-2. Well, 1.40 is positive, so I'm using positive z-scores. That's this table here, or the standard normal distribution. Because remember, with the table that we're using in this case, we have one for positive z-scores and another one for negative z-scores. The 1.4 is the one on the left. For 1.40, we have to look under this column for 0.00. So we cross 1.4 and 0.00, you will get 0.9192. Okay, and that represents this area to the left. Okay, so the probability that x is less than 133 is going to be 0.9192. Now, to interpret this, the probability that a randomly selected adult has an IQ less than 133 would be 0.9192. Okay. Okay, now the next thing I want to talk about is finding the values from known areas, which is similar to the standard normal distribution. So now you're going to be finding your x values from known areas. So here we're finding the values from known areas. Okay? Now, the procedure is just this. You'll sketch the normal curve. So that you can see what's going on. And then you're going to enter the given probability. Sometimes they may give you a percentage, so they all mean the same thing, probability percentage in the appropriate region that you're trying to find. That's what is given to you. Okay, and then you'll identify your x value that you're trying to find. Okay. Now, step number 2. Now, I'm just referring to this, I'm just saying table A-2, which is the standard normal distribution table. For those of you who are watching this, it's the standard normal distribution table. For those of you who are taking my class, it's table A-2. You're going to refer to the body of the table. To find the area to the left of x. Because that table gives you the cumulative area to the left of x. So you want to make sure you want to find that. And then you will identify the z-score. Okay. And then step number 3, okay, after finding your z-score, then convert to the equivalent x value. Using this formula, x is equal to mu plus z, which is a z-score, times sigma. Okay? You'll be given the mean, which is your mu, and you'll be given the standard deviation, which is sigma. Once you find out what z is, you'll use this formula to find out the equivalent value, or the equivalent x value. Okay? So it's just those 3 steps that you have to use. Okay? Now, step number 4, I won't put that there, but I'll mention it anyway. You want to refer to the sketch of the curve and then try to verify that solution to make sure that it makes sense in the context of the graph and in the context of that particular problem. So make sure that you do verify to see if it makes sense. But these 3 steps are just important. Okay. Now let's look at an example of just one of these. In fact, we'll look at a lot of examples. In this case, we want to find the indicated IQ score. The graph to the right depicts IQ scores of adults, and those scores are normally distributed with a mean of 100 and a standard deviation of 15. Okay. Alright, now, this area to the right, I don't know if you can see this, but that's 0.7. Okay, now that's the area to the right. Okay, now if we're going to use the table, we need to find the area to the left. That's this area right here. So you have to do 1 minus 0.7. If you recall, the area underneath the entire curve is 1. So if we know this is 0.7, the area to the left will be 1 minus 0.7, or 0.3. And I'm putting 4 zeros here. Okay? Because our table is to 4 decimal places. Now, 0.3 is less than 1/2. So we need to use the chart for the standard normal distribution that has negative z-scores. Okay? So now, we need to find a number that's closest to 0.3000. Okay, and by looking at this, the one that's closest to 0.3000 would be this number, 0.3015. Okay, so here's 0.3015 right here. Now I'm going to read the row and the column that's in that 0.3015 is in. So the row that 0.3015 is in is negative 0.5, and the column that 0.3015 is in is 0.02. So if I add the negative 0.5 and negative 0.2, now go ahead and say this, your z, that's negative 0.5 plus negative 0.02, you're going to get negative 0.52. That's the z-score. So we'll use z is equal to negative 0.52. Okay? Now we want the x value. Okay? So this is where we use this formula. X is equal to mu plus z times sigma. So in this case here, your mu, in this problem here, let's go back to what the problem states here. Your mean is 100, so that's your mu. Your standard deviation, that's given in the problem, that's 15. So in this case here, your mu is 100 plus z, we found that out to be negative 0.52 times sigma, that's 15. Now, here you can use the calculator and do 100 plus negative 0.52 times 15. Okay. So I'll go ahead and do this on the calculator for you. 100 plus negative 0.52 times 15. And that would give you 92.2. So the x value that you're trying to find here is 92.2. Okay. So that's the IQ score that you were looking for in this case, 92.2. Okay. All right. Here's some more examples of just finding the x values when you're given a known area. Now this one you had to draw a normal curve for this one. Assume that adults have IQ scores that are normally distributed with a mean of 100 and a standard deviation of 20. You want to find P4, that's the 4th percentile. And that's the IQ score separating the bottom 4% from the top 96%. Okay, so in this case here, let's draw a normal curve that looks like this. So P4 would have to be on the left-hand side. And 4%, that's the shaded area right here. And 4% as a decimal, that's going to be 0.04. I'm going to put 2 zeros there because our table has decimal values to 4 decimal places. So this is what we're trying to find. And we're told that the mean is 100 and the standard deviation is 20. Okay. So now we need the z value for 0.0400. And that's less than 0.05, so less than 1/2. So in this case here, we use the negative z-scores and find 0.0400, or a value that's closest to 0.0400. And I'm going to use, in this case, 0.0401. That's this value right here, where my finger is at. Now I'm going to read to the left and up top. I'm going to read off the row and the column that 0.0401 is in. For 0.0401, that row is negative 1.7, and that column is 0.05. So we got negative 1.7 and negative 0.05. So this is negative 1.7 plus negative 0.05. If you add those together, you'll get negative 1.75. So in this case here, your z value is negative 1.75. Now we want the x value. So this is where we use this formula. X is equal to mu plus z times sigma. Your mu is your mean and sigma is your standard deviation. Okay, so using that formula, that x is equal to mu, which is 100, plus z, that's negative 1.75, times sigma, which is 20. And if you do 100 plus negative 1.75 times 20, you're going to end up with an x value of 65 0.00. Okay, so the number 65 represents the value that's in the 4th percentile, and that separates the bottom 4% from the top 96%. Okay. All right, next example. Let's assume that adults have IQ scores that are normally distributed with a mean of 100 and a standard deviation of 15. Now you're going to find the third quartile, which is Q3. And that's the IQ score separating the top 25% from the others. So we're finding Q3. So let's draw a normal curve. And we know the mean is 108. So I'll go ahead and write that down. Mu is 108. The standard deviation is 15. Okay. Separating the top 25%. So your x-ray has to be over here somewhere. And this is the top 25% that I'm shading in green. Okay. So in this case here, if this is 0.2500, and if we use the table, we want the area to the left of that. So this area that's to the left will have to be 1 minus 0.25 or 0.7500. Okay, so we have to use that 0.7500 when we use our standard normal distribution table. And 0.7500 is over 1/2, so we use the z-scores and find numbers that find a decimal value that's closest to 0.7500. And in this case, I'm using 0.7486. Because that's the one that's closest to 0.7500. So we read the row and the column that 0.7486 is in. In this case, 0.6, and then the column is 0.07. So your z is this. 0.6 plus 0.07. That's the row plus the column. That will give me my z-score of 0.67. So that's my z value for this particular situation. But I want x. So x will be mu plus z times sigma. So here x is equal to mu, that's 108, plus z, that's 0.67, times sigma, which is 15. So in this case here, 108 plus 0.67 times 15, that's going to be approximately, to one decimal place, 118.1. So the IQ score that separates the top 25 from the others will be 118.1. Okay, now let's look at another example. This next one is quite long. In fact, the next 3 examples, well, I know this one is quite long. The other 2 are not as bad as this one. Okay. Alright, in this case here, a survey found that women's heights are normally distributed with a mean of 63.6 inches and a standard deviation of 2.3 inches. Okay, this might be a little bit difficult to see. Okay. Survey found that women's heights are normally distributed with a mean of 63.6 inches and a standard deviation of 2.3 inches. A branch of the military requires women's heights to be between 58 inches and 80 inches. Part A is to find the percentage of women's heights. Find the percentage of women meeting the height requirement. Are many women being denied the opportunity to join this branch of the military because they are too short or too tall? Okay, so let's start off by doing part A, and then we'll do part B. Okay, first of all, we need to draw the normal curve. And I'm going to say 58 is over here, and 80 is here, because in the middle, your mu is the center, that's 63.6, and sigma is 2.3. So actually, we're finding the shaded area in between 58 and 80. Okay. Now, each one of those numbers, the 58 and the 80, you have to convert to a z-score. Okay? Or z-value. So here, the z-value on the left for the 58 is going to be this. X, which is 58, minus mu, which is 63.6. All that's divided by sigma, which is 2.3. Okay? In case you've forgotten here, your z is always going to be x minus mu divided by sigma. That's what I'm using here. So 58 minus 63.6 will be, and then divide that by 2.3, that's going to be a negative 2.43. Okay? And the way you can enter that into the calculator, the numerator you'll have to enter in parentheses. So this is like 58 minus 63.6, close parentheses, divided by 2.3, and this is what you'll get, but you have to round your z values to 2 decimal places, so it'll be negative 2.43. And then your z value on the right, that's your 80, your x value, minus 63.6, all divided by 2.3. Remember to put the numerator in parentheses, and then divide by 2.3, you'll get 7.13 as your z-score. Okay. Now we want the area for negative 2.43 and positive 7.13. Okay. Our z-score is negative. So, let's use the standard normal distribution table for negative z-scores. And we're going to look for negative 2.43. Okay. So here's negative 2.4. That's this part on the left-hand side, negative 2.4. And then 0.03 is this column here. So if you read to the right and down, you'll see that it's 0.0075. So for negative 2.43, that area is 0.0075. Now, for the z-score 7.13, this one's a little bit different, because if you were to look under the positive z-scores, you're not going to find 7.13 on here. All right, but you will find a note at the very bottom of this chart, and it clearly states for values of z above 3.49, use 0.9999 for the area. Okay? Here in this case, 7.13 is above the 3.49, so that area is automatically going to be 0.9999. That's what we use for values that are from 3.49 on up. Or any values above 3.49. Okay, so now we have our areas. We can go ahead and find the probabilities. So in this case here, that probability that your x value is between 58 and 80 would be just subtract 0.9999 minus 0.0075, and you're going to get 0.9924. So in this case, the probability that a female's height in the military is between 58 and 80 inches would be 0.9924. Okay, so in other words, 99.24% of the women meet the height requirement. (99.24% of women meet the height requirement. Okay. Now, the other part of that question is, are many women being denied the opportunity to join this branch of the military because the heights, because they are too short or too tall? Okay. And the answer to that is no, because it's only a small percentage. It's less than 1% of the women that fail to meet that requirement. Okay. So only like a little over 0.75%, less than 1%, are denied that particular opportunity to join the military because of their height. So not a lot of women will be denied. Alright, so that's part A. Part B is this. If this branch of military changes the height requirement so that all women are eligible except the shortest 1% and the tallest 2%, what would be the new height requirements? Okay, so now we're going to draw another normal curve. So this will be part B. So now we're looking for the x values here in this case. The x values for the shortest and the x values for the tallest. Okay, so here we're dealing with the tallest 2%, that's the shaded area here, or 0.0200. And on the left, it's the shortest 1%. As a decimal, that would be 0.0100. Now, for each one of these, we have to use the table, A-2, or the standard normal distribution table, and find those z values, and then convert that to an x value. Okay? So let's start off with the shortest height, 0.0100. So you need to look in the body of the table and then find a value that's close to 0.0100. In this case, that I found it, 0.0099. That's a little bit less than 0.0100. So let's use 0.0099. Let's read the row and the column that it's in. In this case, is negative 2.3 and then 3. Okay, so now in this case here, let's say for 0.0100, that z value is going to be negative 2.33. Negative 2.33. And we need to get an x value for the shortest height, which is, of course, mu plus z times sigma. Your mu is still 63.6. That's from the previous example. Well, part A. And that's from the original problem that's given to you. You were given that mu was 63.6 plus z, that's negative 2.33. And you were told the standard deviation was 2.3. So for the shortest height, multiply 63.6 plus negative 2.33 times 2.3, you'll get 58.2. So no, the shortest height is going to be 58.2 inches. Okay. Now next, we need to find the tallest height. So now we need the z value for 0.0200. So we need to know what that z value is going to be. Okay. 0.0200 is less than 1/2, so we use the negative z chart and find the value that's closest to 0.0200. We'll take that back. Want to know why we can't use 0.0200? This right here represents the area to the right. If we're going to use the table, we need the area to the left of 0.0200. So the area to the left is this, 1 minus 0.0200. And that's actually 0.9800. So we have to use 0.9800. And this time we're going to be using a positive z-score. Okay, so now we need to find a number that's close to 0.9800. Let's use 0.9798. I might need to bring that up so you can see that. All right, 0.9798. And to the left of that is going to be 0.20, and that's in the column for 0.05. So it'll be 2.0 and 5. So it'll be 2.05 for your z-score. Okay. And now we use that 2.05 to find out x, the tallest value for x, the height of the tallest person. So in this case here, that's your mu plus z times sigma, which is in this case mu is 63.6 plus z, which is 2.05, times sigma, which is 2.3. And if you multiply all this out, or just punch all that into the calculator, you'll get 68.3. So in this case here, the tallest height will be 68.3. Okay, so based on the new requirements here for this branch of military, the women's heights will have to be between 58.2 inches and 68.3 inches. Okay, if they were to change it so that this will exclude the shortest 1% and the tallest 2%, then those new height requirements will have to be between 58.2 inches and 68.3 inches. Okay. Okay, here's another example. Right, in this case here, the lengths of pregnancies are normally distributed with a mean of 270 days and a standard deviation of 15 days. Find the probability of a pregnancy lasting 309 days or longer. And in part B, if the length of the pregnancy is in the lowest 2%, then the baby is premature. Find the length that separates premature babies from those who are not premature. Okay. In this case here, let's draw a normal curve to see what's going on here. Now, the mean is 270. Standard deviation is 15. 309 is what we're looking at. That's your x value. So 309 is to the right of 270. And we're looking at this shaded area to the right of 309. So in this particular situation here, we need to convert that to a z-score first. So here we use z is equal to x minus mu divided by sigma. Your x value is 309 minus mu, which is 270, divided by sigma, which is 15. So 309 minus 270 will be 39. 39 divided by 15 to 2 decimal places, your z value will be 2.60. Okay. All right. Now we use table A-2. 2.60 is a positive z-score. Now we want to be careful here because we want to find the area to the right. The table gives us the area to the left. So we know we're going to have to do 1 minus whatever that probability value is for 2.60. Well, here's 2.6. 2.6 is right here. 0.00 is here. There's 2.6. And 0.00 is here, so that's going to be 0.9953. Okay. Now that's the area to the left. But the area to the right is going to be 1 minus 0.9953. Okay. Because see, this 0.9953, that represents this area to the right, to the left. We don't want that. We want the area to the right that's shaded in green. So 1 minus 0.9953 will be 0.0047. Okay. So that represents the probability. If it's lasting 309 days or longer, that means x is greater than 309. Or you can say greater than or equal to 309. That would be 0.0047. Okay, so that's part A. Part B is this: if the length of pregnancy is in the lowest 2%, then the baby is premature. And you want to find the length of the baby that separates the premature babies from those that are not premature. Okay, so you're finding the x value in part B. Okay, so let's draw a normal curve. The lowest 2% will be on the left-hand side. So this area on the left-hand side represents the lowest 2%. So in this case here, 2%, that's 0.0200 to 4 decimal places. And this x value is what we're trying to find here. 0.0200 is less than 1/2, so we use negative point, the negative z-scores, and then we're going to find a value that's closest to a 0.0200. And I'm using 0.0202. Okay, so here's 0.0202. Now we're going to read off the row that 0.0202 is in and the column that 0.0202 is in. The row will be negative 2.0 and the column there will be 0.05. So it'll be negative 2.05. So that's going to be your z value. You can write this as negative 2.0 plus negative 0.05, and that's your z value, negative 2.05. And then get the x value. Your x value is this, mu plus z times sigma. Your mu, in this case, was 270. Z is negative 2.05. Sigma is 15. So 270 plus negative 2.05 times 15, which will give you, and if you round this off to the nearest whole number, that'd be 239. So babies that were born before 239 days are considered to be premature. Okay. Okay, and the last example in this video that I will be doing is here engineers wanted to design seats in commercial aircraft so that they are wide enough to fit 95% of all males. Accommodating 100% of males would require very wide seats that would be much too expensive. Men have hip breadths that are normally distributed with a mean of 14.8 inches and a standard deviation of 1.2 inches. Find P95. That's the 95th percentile, meaning you want to find the hip breadth for men that separates the smallest 95% from the largest 5%. Okay, so now we want to find, well, let's draw a normal curve. We're talking about the smallest 95%. So this x value is what we're trying to find here. The smallest 95% is going to be all this shaded area to the left of that x value that we're trying to find. Alright. 95% as a decimal will be 0.9500. And what we want to do here, 0.9500 is a positive, well, it's bigger than 1/2, so we use the positive z-scores of our standard normal distribution. Now, if we use this table right here, there's something down here at the very bottom that tells me what the area is and its z-score. That area that we're trying to find that we have is 0.9500. Look at the very bottom here. You'll see the area of 0.9500. To the left of that, that's your z-score, which is, in this case, 1.645. That's one of those common z-values that we use. Okay? That's a common z-value. For 0.9500, the area is 0.9500. Its z-value is 1.645. So that's a common z-value there. So let's use that. So your z is going to be 1.645. And then to find out what x is, that's where we use the formula x is equal to mu plus z times sigma. Okay, and I need to write down what mu is. Here, mu, you were told, was 14.8 inches. And the standard deviation, sigma, that was 1.2. So using that formula, we have x is equal to mu of 14.8 plus z, that's 1.645 times sigma, which is 1.2. So now you got 14.8 plus 1.645 times 1.2. That will give you approximately 16.8 to one decimal place. So the hip breadth for men that separates the smallest 95% from the largest 5% would be 16.8 inches. Okay. So again, get used to trying to do these types of problems. I do have notes that will be posted on Campus Cruiser for those of you who are taking the class on my campus, and also you're free to email me when you have questions about this. So this concludes this particular video on the applications of normal distributions.